Now let us take this simple system, this spring mass damper system, which you are quite familiar with, and see how we can prepare its model. Okay. So for this system, for this system, uh, we can start with the motion of this end, which is zero. It's fixed. So we have this one junction whose velocity is zero. Okay, representing zero flow. We can then take a one junction here representing the motion of the mass. So we have a one junction representing the motion of the mass, that is v, velocity. So flow is the variable that is associated with mass with this one junction, and all bonds connected to it will have the same flow because it's a common flow junction. It's a one junction. Now, there is a force F acting on this. It moves with the same velocity as the mass. So we assign a bond, we connect a bond to this one junction and model this force as a source of effort uh, with value F of t. It may change. We also have the inertia of this mass. So we have the I element, and because it has the same velocity as that of the, it represents the mass, so it has the same velocity. So we connect it to this one junction. Okay. And now what about the C and R elements? Now you see the relative motion across the C and R elements is the same. The relative velocity is the same. So first task is we determine the relative velocity. Relative velocity is velocity at descent minus velocity at descent. So what we do is we need velocity summation, flow summation. So we employ a zero junction, which is a flow summing junction or a common effort junction. So we say that this flow is equal to this flow minus this flow. Okay. Now what is this flow? It is the velocity v because it's connected to this one junction here. And this flow here is zero because it's connected to this fixed end here. Flow is zero. So this velocity is equal to this velocity minus this velocity, v minus zero. So this is the velocity v. Now this bond can be provided to a one junction because both these elements share the same flow across their ends, common flow. So we make it common using this one junction and connect the C element and the R element to it. So this completes our bond graph model. So what we have got is over here, we have fixed this end by placing a source of flow equal corresponding to zero velocity. It is applied on this one junction so that this end cannot move. Okay, so its velocity has been imposed as zero. So what we have got here is a complete bond graph model. Now let us try to causal this system. So for causaling the system, we always should start with the sources. Okay, so we always start with the sources. So we have two sources here, a source of flow and a source of effort. So we'll start with this source of flow. A causal stroke will be placed here. Now when you place the causal stroke here, when you place this causal stroke here, what happens is this brings in, it brings in flow into this one junction. Only one bond can bring in the information of flow into this one junction. So the other bond has to accept it. It will come here like this. Okay. And then this bond is bringing in flow into the zero junction, but that doesn't help us much because so far we have not caused the other bonds. So we start with this one, this source. It's a source of effort, so we place a causal stroke here. Okay. Now, let me explain it to you step by step. Let me remove this earlier causality so that you all so that you don't get confused or things become very clear to you as we do the explanation. So let us take these causal strokes in red. So we provide a causal stroke here. So this brings in the information of flow. This bond, this junction can bring in only one bond can bring in flow. So the other one has to accept it. Then uh, we don't know how to proceed because here it can have only one bond has been causal. The other two, we don't know how the causality will appear. So we focus on the next the source over here. So if you focus on that, you can place the causal stroke here because it's a source of effort. So it is applying effort on this. Uh, Again, we are stuck here. So now what we will do is start with the start causing the I and C elements. Now we could start either way, either with C or I. So let us start with this I element. Place a causal stroke here. So we'll take a causal stroke. And uh, we will, so a flow has come into this one junction. And now the one junction, all the other bonds have to accept that flow. So we will place the causal stroke here. So now for this one junction, all the bonds have been causal. Now for the zero junction, one bond has brought in flow, the other bond has brought in flow. One bond has to bring in effort. The only remaining bond is here. So we will now, so this one has to bring in information of effort. Then the information of effort has been brought into this zero junction. So here causality is complete. Now here flow has come into this one junction. Automatically the other bonds have to accept that flow. So this bond has to accept this flow. Okay. So it has to bring in effort. And here also this bond has to accept. So this is how the causality for the entire bond graph has been completed. So this is a completely causal bond graph. Now we can also number this bond graph uh, before we number it. We will also discuss about the states contributed by these elements of the system. Now the states are contributed only by the I and the C elements. So here you have an I element. Okay. The state associated with the I element is its momentum, generalized momentum. So P is the generalized momentum associated with this I element. Since there is only one, we are not putting any suffix or anything. So we just leave it as P. There is only one C element also in this bond graph, and that's also going to contribute a state to this system. So we assign the state Q over here because for the C element, the state contributed is always the generalized displacement. Both these elements, you can see they are in proper integral causality, and that is why they can contribute states to the system. We will see a little later in our lectures what happens if this gets violated or if it becomes derivative causality. In that case, uh, how are we to address what happens to the state? Does the element have the ability to contribute the state or not? So that discussion we'll leave for a little later. Then we can, of course, simplify this bond graph. So for simplification, what we have done, we've just taken, you see, we can eliminate this part because it is redundant. The reason being, this is a zero junction. All bonds connected to it have the same information of effort. So if effort is written on each bond connected to this junction, you can write this as E over here. Now, if you see the power that is coming in, here you have E into V, here you have E into V, and here you have E into 0. So you find that there is no power going from this direction, from this bond. So whatever power comes in is the same as the power going here. So this zero junction, it because it has the same effort, information of effort, and also because this is a velocity, the same velocity. So you can directly couple this to this one junction to this. You can eliminate this zero junction. And placing this one junction directly over here is like uh, making it like this. Okay, so you just switch this, you switch it over here, remove that zero junction to get this. Okay, so this is now a simpler way, but again you see that this one junction and this one junction, they represent the same thing. Okay, so you can simplify it like this. Directly you can place this one junction here. So you're left with this. Now there are a few variables and efforts and flows. They are represented on the bonds. How did we get them? That's what we'll discuss. So if you look at these efforts and flows, you'll see that the power comes into this system brought in by f of t. So you have f of t and you have F3 equal to V. So you see I have numbered the bonds also over here. 1, 2, 3, 4. This is arbitrary numbering. It's just to have some identification. So here you have the force F of t and you have the velocity of the mass. Now what is this velocity? We'll just come to shortly. So we have got the effort and the flow represented here. Then if you look at this bond here connected to the I element, it has an effort and a flow. The effort is the rate of change of momentum. P2 is equal to P2 dot. P is the momentum associated with this I element. So it is P dot in this case, P and P dot. So the I element is going to provide flow, which is the velocity, which is equal to P upon M given by V. The velocity associated with this mass. So you have got the effort and the flow shown here. Then we come to this spring, the bond connected to the spring. If you represent the effort and flow, you can see the flow is the same because it's connected to this one junction, and flow is flow F1, which is coming from flow 2, which is P upon M, because all bonds connected to this one junction have the same flow. So V is P upon M. F1 is the same as V, which is P upon M. So we know flow, okay? And here we have the effort, which is depending upon the characteristic of the spring. If the spring is hard, K will be larger. So E1, that is the effort applied by the spring, is equal to K into Q. So this is as far as the effort and flow of bond connected to the C element is concerned. Similarly, you also have the effort and the flow connected to this R element, bond on this R element. So here flow is of course same as V, P upon M, and the effort is E4, that is R multiplied by V, R multiplied by the flow. Okay, so effort 4 is equal to R multiplied. You can see that in this figure, we have all variables of power, that is the efforts and the flows written in terms of respective states and parameters. Okay. You can also write these equations in a form which we call as a state space form. You can write this as P dot this effort. So it's an effort summing junction. So you can say that this effort is equal to this effort minus this effort minus this effort. So this effort is equal to P2 dot, and that is equal to F3 F F of t minus R into V minus K into Q. Okay. So when you simplify it, it looks like this. When you write it in terms, if you replace R into V, you can write it as R into P upon M. So on the right hand side, you just have the states and parameters. P and Q are the states. R, M, K, these are parameters. And this V, velocity V, is equal to Q dot, and that is equal to P upon M. That is the second equation. That is Q dot, this velocity, rate of change of this state, and that is equal to P upon M, because this velocity is being decided by this mass as a function of its state, which is the momentum. So Q dot is equal to P upon M. So you see there are these two equations only for this system. We will come to the process of derivation of system equations a little later.